Hey everybody, welcome to the MGS Brown Bags. I think we'll get started. I'll go ahead with Jessica's introduction. Jessica Marggraf is with us today. She's currently a postdoc research associate at the Department of Earth and Environmental Sciences at St. Anthony Falls Lab at the U of M. Her research interests are fluvial processes and evolution across spatial and temporal scales and their measurement methods. Before joining the U of M, Jessica completed her PhD at INRAE in France on sediment transport and monitoring techniques. She holds a master's in engineering and geosciences for the environment from the University of Strasbourg, France, and a bachelor in geosciences from the University of Freiburg in Germany. And today she will be presenting on the control of lithology in base level fall on fluvial erosion along the Minnesota North Shore. So go ahead, Jessica, and take it away.
Okay, yeah, thank you for introduction and thanks for having me. So with my coworkers at UMN, Duluth, and University of Lorraine, we're working, as you just said, on the control of lithology, on base level fall, on fluvial erosion, on the North Shore of Minnesota. Here you can already see two of the very nice pictures from the different rivers and the waterfalls where we have been working on. So when you're talking about rivers and the river evolution, we're usually interested in river long profiles and how they have been changing with time and also why they are changing. And so typically river profiles, they kind of just record the elevation of the river related to the distance from its base level, like an ocean or a lake. And usually we have these kind of profiles, as you can see up here, with very steep headwaters and then lower and lower slopes when reaching the base level, in this case, the ocean. However, these profiles are also very interesting for us as geomorphologists because they record information on tectonics and climate, for example, a base level fall. Just here, again, an example, with this case, the ocean on the level or the lake on the left side. So we have this elevation, the river long profile. And in this case, if our base level is falling, dropping, related to multiple different reasons, recreating first a very steep nick point, what we call nick point with waterfalls, for example, close to this base level fall, close to the lake shore or the ocean front. And then with the time, this nick point, so this zone of high slopes, is further moving upstream, this kind of being a focal point of erosion that is transiting, migrating upstream. And in these areas here, where we have these high slopes, we often have bedrock that is outcropping, and also we have a lot of waterfalls, bedrock gorges. And what we are interested in are also the processes that are occurring at these nick points, at these nick zones. And in bedrock rivers, there are two main processes that are performing the erosion usually. There's one, abrasion or impact erosion. So as you can see here on these schematics, you have like bedload, pebbles or gravels that are siltating on the bed and thus impacting the riverbed. And through these multiple impacts, they are chipping off small parts of the bedrock and thus smoothing and abrading the bedrock. And of course, as you can imagine, the magnitude of this process depends a lot on the strength of the bedrock. So softer rocks eroding much faster than harder rocks. It depends also on the availability of the sediment pebbles, the bed load, so what we call tools, and also on the cover. So if you do have so much sediment that almost all bedrock is covered, we will not have much erosion because the tools cannot even reach the bedrock. There is this kind of interplay between the availability of tools and the cover. And as we can already have bed load transport for rather low discharges, so we can already have abrasion, also it's very small, at very low discharges. So we can more imagine abrasion is kind of a more continuous process that is occurring kind of continuously as soon as we have bed load transport or also sometimes suspension transport. And then, as you can see here on this picture, we have these kind of sculpted bed forms, these kind of smooth surfaces. The second process is plucking, where we have different blocks of usually larger sizes, different decimeters, centimeters of size, that are bound by fractures and kind of sitting on the bedrock, and they are then entrained by the flow. So here, just either being toppled over or being sliding down a slope. And as you can imagine, for these larger blocks, we need already much more energy by the river, so much higher discharges that are required to move these blocks and also entrain them. So here, plucking depends a lot on the frequency as well as the magnitude of these kind of flood events and thus the plucking events. So this has much more an episodic or random character because it's much more related to floods and high flow events. And in contrast to abrasion, you can see here on this picture already these kind of sharp surfaces and more like fracture bound. You can even imagine that they were before kind of blocks sitting there and they were just being removed. So it's these more like fresh surfaces that are looking like this, much rawer and harsher for the plucking processes. So those are observations from the field and from the theory. And if we want to measure these erosion rates, both for abrasion and plucking, we can use, for example, different laboratory experiments. So here are two examples how to measure abrasion. That's our impact erosion. So here on the top, those are so-called abrasion mills. So we have here a small part, kind of a disk of bedrock that is exposed, and then having glass beds or other material that are current for a very long time, so several months in this case, and then frequently measuring the abrasion rate, so kind of how much the bedrock has lost in mass or material. Another possibility, if you don't want to wait for several months to get some results, is a similar setup, also kind of a circular mill as down here, where we just, in this case, use different pebbles. So you can see here a bit on the left, add some water, then have the pebbles moving around in a circle in kind of a washing machine style. So we then have, in this case, having the pebbles hitting each other and thus not abrading the bed, but actually themselves. So in this case, we rather have attrition, but which needs to be scaled to obtain the abrasion rate. But at the same time, the big advantage is that it's much faster. So it's going to have just like an hour or so to get some useful results in comparison to the other ones. So this one's just being said for abrasion. And as example for plucking, there are much less experiments that have been done. They're also much more complicated because there's relation with the discharge. Here just a few examples where they used some kind of small cement and plaster blocks that are then being either slided or in this case kind of toppled over for these experiments. And now when we want to relate this with information on the bedrock, so how they may have been related to the strength, for example, or fracture intensity with the bedrock, in case of impact erosion or abrasion, it is often related with the tensile strength and in many literature, in many studies, often with the inverse square. So here is an example of a compilation of different data, including the experimental erosion rate compared to the tensile strength of the rock. And you can see here already that there is a lot of variability, so several orders of magnitude in the experimental erosion rate compared to for one single tensile strength. And one recent study does focus more on this and proposed a new equation, not only accounting for the tensile strength only, but also including the Young's modulus, here used as y. And based on this equation, they suggest that there should be rather a linear relation with the tensile strength instead of the squared relation that has been typically used in the literature. And with this, we still see also this variability of several orders of magnitude, and also it remains still unclear if there's a square or a linear relation. And moreover, if you want to dig further into this impact erosion or abrasion, so we can also focus on the grain size of these different erosion products. So for example, we are interested in if the particles that are being eroded, so these are that are being chipped off, are small particles like ware-like particles, smaller than sand, like sand grain sizes are smaller, so smaller than 2 millimeters in diameter. Or if they are much larger, so more like fragments or gravels, larger than 2 millimeters. So for this, there has been a study focusing exactly on the difference relating the mean fragment diameter, as I just explained, with the impact energy. So how strong the impact is compared to the diameter of that impactor, like the pebble class, for example, that is hitting the bedrock. And what they found out was that for a certain grain size, all the product, or for a certain impact energy, all the products that are being chipped off are wear-sized particles, attrition-sized particles that are sand-sized particles or smaller. All the ones that are up here on this kind of left side, center part of the diagram. And once you exceed a certain transition zone, certain threshold kind of, in terms of mean kinetic impact energy density, they obtained much larger fragments and gravels in their experiments, so that in this case, they made a separation between the small sized particles and also the larger fragments, what is called macro abrasion. However, so we see this dependence on the kinetic impact energy density, but also in their experiments, for example, they mostly used homogeneous materials, kind of artificial sandstone. And so it remains unclear what the influence of different material properties or also heterogeneity might be. So just to recapitulate what we've seen on the different erosion processes. So I was already talking about plucking and impact erosion or abrasion. And so if we want to have a look further into abrasion, we can separate this, as we've just seen before, for the micro abrasion, where we, for example, have multiple bed load impacts, and then creating fracture propagation, crack propagation, which is then creating a fragment larger than like fragment size or pebble size, which is then being chipped off. In contrast, for macro abrasion, we might also have these like small crack propagation through multiple impacts, but what is the main difference? It is mostly limited to the contact zone where the pebble was impacting, and we have much smaller erosion products like sand or silt size, and they're also often related to only one single grain. So just this to recapitulate the different processes. And now if we have a look on our study area, as I've been talking before about the Minnesota North Shore. So as most of you probably know, the Minnesota North Shore is part of the Mid-Continent Rift. So we have a lot of different volcanic and igneous rocks up here. And for this study, we have been looking at 6 different rivers, namely the most important ones were Cascade, Temperance, and Gooseberry rivers, where I'll also be talking about in the further of this presentation. And we see different lithologies in this catchment, mostly diabase, basalts, icelandite, as well as sandstone as the only sedimentary unit we have been looking at. And what is also interesting, as you can see here, I separated the basalt top and the central part is, so all these basalt flows from the Mid-Continent Rift, most of them exhibit a very clear internal structure, which is related to the cooling of the basalt flows. So we had a lot of vesicles that were then later infilled, creating what we call amygdals then. And so at this top part, related to this cooling, we have this amygdaloidal kind of bubbly structure, whereas the central part of the basalt column is much more homogeneous, much more massive, as you can see here in this picture again. And why we're interested in the North Shore here in Minnesota and the rivers in this area is related to the evolution of this base level. So as I've been saying in the beginning, here, this is exactly an area where we had a base level fall, which has been recorded since the last glacial retreat, with several lake level drops of the Paleo Lake Superior, like for example, Lake Duluth, led to several lake level drops, about 200 or 140 meters in total, and thus creating not only a set of strand lines, but also being the onset of the incision of the rivers, as is our hypothesis, about 10.6, 10.8 thousand years ago, and then sending this signal of this rapid base level further upstream, so that we then have this migration of our Nick zones upstream. So related to this, I just want to present two main goals of our research I'm going to talk about today. Is first, more related to the processes themselves. So trying to understand how lithological properties such as compressive strength or rock strength, fracture intensity, and block size, are influencing controlling impact erosion, thus abrasion. And for the second part, really related to the North Shore rivers, so how they have been evolving since the last glacial maximum, or since the glacial retreat, more specifically. And to answer those questions, I will be combining field and flume measurements with geospatial analysis and soon chlorine-36 dating. So let's have a look at what we have been doing and focus first on this erosion processes part. Here, using a combination of field experiments and flume experiments. So first now, for the field measurements, so we measured 10 different lithologies, and for each of these lithologies, we performed several survey points along the river on these outcrops, and for each of these survey points, we collected information on fracture properties and rock strength. So first, we performed 25 Schmidt-Hammer measurements for each of those, and then which can be used as a proxy for compressive strength or for tensile strength. And then we also took pictures on which we then traced these fractures, as you can see up here, and then used the image analysis software FracPack, which is often used in structural geology, to get information on fracture intensity and also the block size, thus relating it potentially to plucking. In addition to these field measurements, as I already said, we performed flume experiments, and we actually used this circular flume I was showing in the beginning, where we had like different pebbles hitting each other, thus performing an attrition. And this one is available. These experiments were done at the University of Lorraine with Jérôme Lavie. And here they use two different types of flumes, a small and a large flume, with a higher pebble and water velocity and also higher pebble diameter in the large flume compared to the small flume. So in this case, we can then reach higher impact energies in the larger flume than the small flume, just to be able to explore a larger range of different conditions. And also on these pictures up here, you can see two different lithologies on the top and the bottom row. First before the run and also then after the run, you can already see that they are much more rounded, or may also have been fragmenting as those two pebbles up here. And they have some kind of standard protocol, what they are using all the time for their measurements. They have been performing them since about 20 years now. So they have like the protocol they're always following. And for this, they use specific pebbles of an abrading lithology, for example, granite or autogneiss, just to perform the erosive work and then be able to compare it with other experiments. So now, let's have a look at our results. And as I've been saying in the beginning, so we had this relation from the attrition with compressive strength, where earlier studies found increasing attrition with decreasing compressive or tensile strength. Let's see how this is looking like in our results. So here we see the attrition rate measured in the small flume compared to the compressive strength measured in the field. What we can already see here is that we have this very clear relation, this linear relation in some of these lithologies. And those lithologies are the ones with basalts mostly found at the Gooseberry River, so in these blue colors, where we have also very large block sizes, as you can see on this picture. And then there's some other lithologies down here, some other different measurement points, where it seems like that compressive strength alone is not able to explain the attrition rate. So the erosion rate we measured actually in the flume. Even so, we take account for the variability, for example, from our field measurement with the Schmidt-Hammer, or also other potential variabilities. So let's have a look what might be potentially explain this difference. So here again, on the left side, the same plot we've just seen with the attrition rate compared to the compressive strength. And now I just added information on our fracture properties, one's a fracture intensity as well as the block size. And so for the ones that are well aligning, so these blue ones mostly, those are the ones that have very low fracture intensity, thus having these large blocks as we've seen before in the pictures. And in contrast, the other ones, mostly the Icelandite, the diabase, also one of the basalts from Leicester River, those are the ones where we see higher fracture intensities and also smaller block sizes. So we see this difference where potentially the fractures may have an influence on our measurements, for example, in the field with the Schmidt hammer, because we're not necessarily seeing if there are any fractures further down in the bedrock. Then we're just hitting these fractures when you're measuring, and thus kind of decreasing, for example, the value of our compressive strength measurements. Because also our Schmidt hammer measurements are kind of in general sensitive to different rock properties in total as well. Okay, now if we want to have a look at macro abrasion, so these particles, the same process with the impact erosion, but the particles that are being chipped off are much larger, so we have these fragments instead of before having sand and silt-sized particles. So here for this one, we see again the macro abrasion rate for all of the 10 different lithologies. And here for the large flume, we performed the first run where we're supposed to round the different pebbles, and then a second run with the already rounded pebbles. So we want first have also the potential influence of the particle shape. So here you can see the results of the first run in the large flume, measuring the macro abrasion rate. And what you can see is mostly that the highest values are the ones in the top of the basalt flows. So these vesicular amygdaloid edal parts with these kind of raw surfaces that are usually exposed. And then how here you can see, for example, on the left side a thin section, and then on the right, a picture how these lithologies are looking like in the field. So we really see all these amygdals that are also traced here on the left, which are then creating this kind of variability related to the heterogeneity. Well, and if you have a look at the results of the second run, so now these bold symbols, there are just 3 of them. So we only had macro abrasion that occurred in more fine-grained lithologies, such as the Icelandite or also the sandstone in this second run, where we already had these rounded particles. So this just shows us that the macro abrasion really depends on structural weaknesses, such as the amygdals, but also on the texture, as we've seen with the fine-grained lithologies, and also relates to the shape between, thus this difference between the first and the second run. However, we did not find any relation with the rock strength, like compressive or tensile strength, or the fracture properties, where we did see these relations before on the attrition or like the fine-grained impact erosion. So now we've had separate looks on attrition and macro abrasion. So let's compare now with the literature and potential relations also with the energy that is occurring. So I'm just showing the same plot as I was showing you in the beginning. So relating here the attrition rate, so this fine-grained impact erosion with the tensile strength, and the compilation of the data from the literature we've seen in the beginning, plus overlying with our data here in the color. So these empty symbols here in the top are the ones from the large flume, where we have higher energy. So for the same lithologies, measured in the large flume, we find much higher attrition rates, higher erosion rates than in the small flume, where we have lower energy. So just being able to compare 2 experimental setups with 2 impact energies for the same rock shows us that there is a big influence actually from the experimental setup on such a kind of a relation up here. In the experimental setup, it's not only to the kinetic impact energy, but also on the impact statistics. It depends. So how often pebbles, for example, are being able to hit each other and with which velocity. So this just shows that all these different studies, not using the same instruments, but using different setups, present all these different variability, and that we should not, for example, here, expect that everything will be collapsing perfectly on one real perfect relation, but that there is this independence on the impact properties, which we can then also assume in the field, for example, in relation to flood properties or per percentage of bed load or bed load transport. And so in this part here, focusing also on the attrition rate. So if we then compare again influence of the kinetic impact energy, as we've seen here before. Here, using the kinetic impact energy and just normalizing it with the diameter of the impactor. So if you have large or small particles that are hitting the bedrock, and then relating it with the mean fragment diameter, kind of the same diagram as before, where we had the literature showed that there is a very thin transition zone between microabrasion and the macroabrasion regime. And our experiments showed were situated here for the small flume in terms of mean kinetic impact energy density, and here for the large flume. So that's much lower than the experiments in the literature that were producing macroabrasion. And in our experiment, we've definitely seen macroabrasion, so fragments being chipped off at these low impact energy densities. Mostly, we assume that this relates to the heterogeneity of our rocks, mostly in terms of different textures, or also the amygdals, but also fractures or the different shapes that are just much more different than the homogeneous artificial sandstones that were used in this study, establishing this very thin transition zone. So just to highlight here the impact of the heterogeneity of natural rocks compared or on the different impact erosion regimes. So now we have a look on the different processes, more in detail relating field and flume measurements. Now let's have a look how we can thus identify or what these processes can tell us on the story of the North Shore rivers since the last glacial retreat. So for this, I'll be focusing again on Gooseberry Temperance Cascade River as well as Catface Creek, where some of you might probably know those rivers, especially the waterfalls. It's kind of famous up there. So just a quick view again on the methods before getting into. So for the field measurements, we kind of did exactly the same as for before, just expanding on other rivers as well, with Schmidt-Hammond rock strengths as well as fracture properties. In addition, we performed terrace mapping, so just manually mapping the different terraces to get surfaces that are as pristine as possible, so not being altered, and so being able to retrieve really the original terrace surfaces. And here we divided into bedrock terraces and alluvial terraces as far as this was possible, based on visual inspection or some of the inspection in the field. We also collected data for chlorine-36 exposure dating. We'll be doing this on hull rock basalt, and I hope to have the data by this presentation. That's why I chose the very late date for the presentation here in April. But of course, they're not here, as always, I think, for any presentation. So I would just talk about our hypothesis and then our sampling strategy and what we potentially hope to get out of that for this exposure dating technique. So again, let's have a look at the river long profiles here for Gooseberry, Cascade, Gooseberry, and Temperance River. And you can already see that these profiles with Lake Superior here on the right side, they are looking so much different than kind of the standard profile I was showing in the beginning with these steep headwaters. Here, we really have the highest slopes close to the lake shore, and it's really this convex shape we usually don't see in rivers. And for this, in the following, we will be focusing on these areas close to the lake shore where we have also bedrock outcropping, as we here are interested in the bedrock erosion processes. So now let's start with the Cascade River and then zoom in these last 6 kilometers close to the lake shore. So what we can see here, so we see this profile, but we can also see different terraces that are mapped and the respective elevations above the river long profile. And so we have two sections where bedrock is outcropping. This first one close to the lake shore, which is also this kind of main gorges area, very close to the highway if you're visiting that. And then another one much further upstream, about 5 kilometers, where we also have, again, bedrock that is outcropping, bedrock gorges. And so we really have these two different sections along Cascade River. And if we observe that a bit more, also perform some measurements, we see that there is much softer basalt on this third upstream nick point, nick zone, the blocks are much smaller and the valley is much wider. It is more looking a bit like this up here, whereas on the lower downstream bedrock gorge, we find much more harder basalt, the blocks are larger, and the valley is much narrower. And the valley is much narrower. So you really see this difference in between the two sections, and thus also the relation of the rock strength and fracture measurements and the valley width. So we can also already hypothesize on different processes that are occurring. So if we have thus small block sizes, we can have potentially more plucking in this upstream area. So now having a look at the similar profile now for the other rivers. So first here for Cutface Creek, and I added a few other information on this one here. So again, the elevation of the river compared to the distance from the lake shore with Lake Superior here on the right. And here you can already see that there are not that many terraces. They're not as high as in Cutface Creek. And we also see bedrock terraces also in this upper area, and we see alluvial terraces in the lower downstream area. And I colored a little bit the line. So in this lower part, we see this Cutface Creek sandstone here in pink, and then the upper part with the basalt that is outcropping up here. So we also see a bit this difference in the slope. So we have, again, this kind of distinction with these two nick zones, one closer to the lakeshore, and then a second one further up here, where we have this stronger slope, thus higher, kind of stronger nick point. What is interesting, I colored above with these points, they are showing the rebound factor, so not converted, measured by the Schmidt hammer. And interestingly, we see in this lower zone, lower area down here, both for the sandstone as well as for the basalts, we see much lower rebound factors, that's much weaker rocks than more upstream with this, where we in the basalt, more in the nick zone with these higher slopes and thus higher rebound values. Might potentially relate to a longer exposition, also to longer exposure, or also to some kind of further alteration of the basalts, for example. Here, just an example, picture of the sandstone. It is very fractured, very soft. And then the basalt from these gorges, which are relatively narrow, on some of the terraces a bit on the side. Now, let's have also a look at the Temperance River. Similar figure, including the alluvial terraces and the bedrock terraces. In this river, we see very well-defined terraces. We see two terrace elevations in kind of three zones with nick points, one close to the lake shore, then the other kind of main area with this very famous narrow gorge, and then a second or third one further upstream. And as I was already saying, so we see these two terrace elevations both in the bedrock terraces, but also here in the alluvial terraces, in the central in both of these parts. And it's also clearly visible in the field. So here, one of these main viewpoints in the center of these two terrace elevations. And what you can already see on this picture here is that these terrace elevations are corresponding well to the surfaces of the basalt flows. So we can easily identify these two different basalt flows in this area, and then also kind of an intermediate layer or thin top layer that is kind of the top of that terrace up here. And just a few words about our chlorine 36 sampling strategy, because it's so nice to see that here on Temperance River with these nicely developed terraces. So we usually, we collected samples at both terrace elevations, kind of really vertically aligned, and did this on the upstream section, as well as on different locations in that main area, as well as downstream close to the lake shore. And in this area, the goal here was really to be able to determine kind of a vertical insertion rate and a horizontal retreat rate. So through these samples, we really try to understand if the incision, so if the whole area was at a higher elevation, so forming the upper terrace, and then completely incising, creating the second terrace level, and then incising again to reach today's level, or if it was more like a wave migrating upstream, and through this creating also the different nick zones. What will also be interesting to see is, because we always, in all of the rivers, we see these two nick zones, one close to the lake shore and one further upstream. So we really want to understand as well if this upstream nick zone, if it's much older, or if it was created by the same event about 10.6 to 10.8 thousand years ago through this base level drop, or if it's kind of relating to some paleotopography, to some exposure from previous events, or if it's like the same one. So with this, we hope to get some information once we have the dates from a little bit more back. So just quick info about that. Now, if we have a look again at our terraces, and here what we can see in the field is that these, except that the terrace elevations are corresponding to the basalt flows, we don't see really such an internal structure of the basalt flows between the top of the flow with these amygdals and the more massive or central part of the flow. However, if we then zoom in a bit more, if you're looking downstream from the top of the kind of middle or downstream bedrock section, what we can see here is again different basalt flows. Here, top one, the central one, which is more defined, and then another one that is kind of here forming this kind of small elevation next to the river. So we can see that between these different basalt layers, basalt flows, there's also always this undercutting. We see really this that the river was like eroding much faster, being able to erode much faster in these areas. And those are the layers where we see much lower compressive strength, also much higher fracture density. They're very thinly bedded reddish layers with a lot of amygdals in between these layers. So here we really suppose that we had much more undercutting by the river, and then a toppling over of the basalt columns, for example, which is then creating this kind of steep, almost nearly vertical walls, and the surfaces are usually corresponding also to the cooling fractures of our basalt columns from these basalt flows. We can also in some areas see this, that we have overtoppled blocks. We still see like the shapes or also these sharp edges that are still being visible. So that's kind of a combination between the fluvial erosion with the undercutting and then facilitating this toppling over of the basalt columns by, for example, fluvial influence or also gravitational influence. And so all these points here, what we are, these colors points up here are measurements with our Schmidt hammer, and just designing in this case like compressive strength values. And if you have a clear look on that, we see that the darkest, the most reddish dots correspond to the highest values of compressive strength, and they are located on the most freshest surfaces. So the most recently abraded ones, we still have these kind of sculpted forms in this central part here, or here on the side. And then you kind of the tendons, if you go further high, if you go much higher, the compressive strength values decrease. So we see that decreasing compressive strength with an increasing elevation above the river, which can then give us a relative idea of the terrace elevation, the terrace age, because you have much more weathering on this top part up here. So that's also why Schmidt hammer rebound values or compressive strengths are frequently used as kind of a dating technique or relative dating to date different landforms using the weathering effect, for example. And now let's have a look at the last river in this case, the Gooseberry River. We see again, you've already noticed, I suppose, these two bedrock sections. The main area with the main falls here in the lower part, where we have bedrock terraces or bedrock outcropping, and then the fifth falls area further upstream here. And here, what is nice to see is close in this main falls area, we really see like this depth, like topography. And the elevate or like the dipping of the river really corresponds also, it's flowing along the top of one of the basalt flows and showing this typical dip of about 10 to 15% towards the center of Lake Superior. That's the central part of the mid-continental rift. And that's what we can see here with our river elevation as well. And also what is interesting with these two elevations is that we have depositions not only of glacial lake sediments or glacial till, but we also found glacial striations at two different elevations. One just upstream the first like main nick zone above the upper falls, and one above the fifth falls. So those are in today's riverbed, as you can see on this picture, but it's in a band that is eroding and cutting into the deposits, the glacial lake or glacial till deposits. So those are freshly exposed surfaces that are showing that these surfaces up here and up here were already exposed to the glaciers that could then create these striations. So just giving more a hint to our hypothesis that those are nick points that are originating from two different cycles. So the upper nick point is potentially older than the younger one. And what is also nice about the gooseberry, we focus more on the erosion processes again, is that we can really see such a clear influence of the internal structure of the basalt flows. So here an example from one of the kind of vertical walls around the pools of the gooseberry, like the lower falls. So we see this distinction from between the top, the amygdaloidal top of the basalt flows, and this much more massive homogeneous center or bottom part of the basalt flows. You can also see some of these cooling factors giving kind of during these basalt columns, the hexagonal columns. And also between the top and the bottom of the flow, we see such a distinction as we can kind of expect already in the compressive strength. So the massive bottom part is much harder, much more resistant than the amygdaloidal top part of the basalt flow. And same for the fracture density and the mean block size. So the blocks are much larger in the top part of the basalt flows, where we really have these large hexagonal basalt columns, as you've seen a few times on this in the pictures today. And in contrast, in the bottom, the massive part, we sometimes also have like the cooling fractures coming from below and from above, that's kind of intersecting, and the bit that's creating like smaller blocks or smaller columns. So we have smaller block sizes and this much more harder lithology in the bottom part of the basalt layer. Now, relating these measurements, there's the visual observation from our river. So here, an example from the falls, from Gooseberry River. Here we can see kind of clearly three different basalt flows, one here at the top, the central one, and then just apart from the lower one down here. And we can also relate it here with the different erosion processes like abrasion, impact erosion with plucking and plucking. So in the top part, we can see here these very sharp surfaces, the nearly kind of vertical walls, which are corresponding also to the cooling fractures of the basalt the basalt flow and these kind of columns. And they're looking like more like fresh surfaces. And in this area, they also kind of tilt a little bit downstream as related to the dip of the basalt columns, the basalt flows in total. And here we can really see that these areas are much more dominated by the plucking, just by related to this observation, which are more in the bottom of the basalt flow. We can see it a bit similar down here with also, again, this kind of structure. In contrast, the top of the basalt flow, as you can see here in the lower part, it's much more raw surface. We see these low slopes, not as steep and vertical. Here we see much more macro abrasion, as is related to our experimental results, where we really had these impacts and then chipping off small fragments. But in some areas, we see also here a little bit from the side here, actually a pothole or some kind of sculpted bed forms. here our observation just shows that potholes mostly originate in the top parts of the basalt floor, for example, at the intersection of the different basalt columns, and then they are quickly eroding on the top part because it's much softer, and then eroding down further downward into the massive bottom part of the basalt flow, where then they are being able to expand through the abrasion, but also being more like blocked because it takes much more time to really erode the more massive central part of the basalt flows. So now, to summarize what we found out is mostly that lithological properties, and in particular heterogeneities, are really impacting the impact erosion processes, like abrasion processes. So we found that large blocks usually compressive strength relates well to microabrasion, the attrition we measured, and when we have small block sizes in these lithologies, the fractures do influence the compressive strength and the microabrasion rate. And this also relates a lot to the internal structure of the basalt floors. So where we really see this impact of the heterogeneity through the amygdals and the texture, but also a bit through the shape, so that we have much more macroabrasion in the top part of the basalt floors. And the central bottom part, the massive part, we found more microabrasion, kind of the attrition in our experimental results, or also if we have a larger scale, which we're not measuring, which we're able to measure in the experiments, but we're able to observe in the field, that if the block sizes are small enough, that there is likely a lot of plucking, and thus forming really this kind of step-like texture or this step-like topography, as for example in gooseberry. And with this, we see this whole study of our findings as a step further towards understanding the erosion processes in general as some kind of a process continuum, which will then be able to understand the process dominance as well. So if we understand this as an interplay between abrasion on one side and then plucking on the other side, it really depends a lot, not only on the geological settings, so the lithological properties, what we've been talking a lot about, but also on flow dynamics that's related to the kinetic impact energy or the impact statistics, and that's related to the flood and plucking frequencies and magnitude or the block dimensions. Just trying to understand how we can further move towards an understanding of which erosion process is dominating and why. And with this, I would like to thank everyone who has been helping in the field or through some discussions, as well as you for being here and for your attention.